Modern artificial intelligence systems rely on rigid silicon processors. Biological intelligence, however, operates as a fluid, distributed network. The human brain achieves language, memory, and spatial reasoning on a metabolic budget of approximately 20 watts. By comparison, engineered AI models require server farms the size of city blocks, consuming megawatts of power. Current computational models rely on a centralized metaphor. A master processor pulls data from global memory states, calculates an output, and writes it back. A new mathematical framework called Distributed Autonomous Neuron Theory, or DAN, provides a rigorous proof for how biological cognition bypasses this massive energy bottleneck. The framework rests on a single foundational axiom: cognition emerges exclusively from decentralized, local interactions between autonomous agents. Individual neurons are semantically inert in isolation. In this system, there is no master orchestrator. There is no global clock dictating computation cycles, and no centralized database storing memories. To replicate true general intelligence, we must stop building top-down calculators and start engineering self-modifying autonomous graphs. To understand the mechanics of this graph, we must isolate a single mathematical node and examine its internal architecture. This maps the local state of an autonomous neuron. It tracks 4 parameters: the incoming signal X, internal synaptic weights W, locally stored data D, and a probability distribution P over neighbors. Information flows via a locally gated recurrent unit, passing through specific filtering matrices before generating an output. The update gate determines how much past state data the neuron retains versus rewrites. The reset gate controls how much past state influences the current prediction. This architecture maintains stable memory while remaining responsive. When a prediction is wrong, an error signal flows backward from a downstream neighbor, forcing the node to adjust its internal weights. This local gradient descent occurs entirely within the node's local boundary. No gradient information ever arrives from non-neighboring nodes, and there is no global loss function monitoring the network. By ensuring that a node can optimize its parameters using only immediate neighbor feedback, the LGRU system satisfies the requirement for total computational autonomy. Once a node processes an input, it connects to a limited subset of adjacent downstream neurons. This visualizes the probability distribution the node generates before firing, ranking possible neighbors. Probability combines 3 variables: existing synaptic weight, contextual relevance, and global neuromodulators acting as emotional bias. The variable controlling this randomness is temperature. When temperature rises, the distribution flattens, equalizing odds across all potential pathways. When temperature is low, the selection process is highly deterministic. The signal rigidly follows high-weight pathways, producing fast, predictable, habitual responses. When temperature is high, the node is forced to sample stochastically. The signal explores weaker, less active pathways, deviating from expected patterns. When a node samples from these lower probability neighbors, it breaks the deterministic chain, allowing the signal to traverse a combination of nodes that has never fired together before. Multiply that local routing by billions of nodes, and you get a chaotic graph, where thousands of distinct thought traversals execute simultaneously. This parallel execution introduces contextual superposition. A single neuron participates in multiple, completely unrelated cognitive tasks at the exact same time. For example, a shared neuron in the prefrontal cortex can act simultaneously as a motor planning variable for steering a car and a linguistic variable for maintaining a conversation. This presents the classical binding problem. How does that shared neuron mathematically isolate its linguistic context from its motor context, given there is no central traffic controller assigning its roles? This is the phase coherence operator. It resolves the binding problem using timing instead of physical location. Neurons in a specific thought process lock their spike timings into the 40 Hz gamma band. Once synced, they form a coherent subassembly within the wider graph. This rhythmic synchronization dynamically isolates specific subgraphs. Time itself acts as the contextual relevance parameter. Meaning inside a neural network is not a physical location in a database. It is a temporary state of temporal synchronization, completely dissolving the need for essential orchestrator. Without essential orchestrator, the architecture has to explain how a decentralized thought process knows when a task is finished. This tracks the Lyapunov's system energy equation, measuring aggregate instability across an active neural assembly. Local free energy is a node's prediction error minus its exploration entropy. High error equals high system energy. Each time an individual node adjusts its local weights to reduce prediction error, the aggregate energy of the entire assembly strictly slides downward. Eventually, the assembly reaches fixed point convergence. The local error gradients hit zero and the physical system stabilizes. Because each node continuously monitors its own energy state, it independently detects this zero gradient condition and ceases firing. Cognitive task termination is an emergent physical guarantee of thermodynamic descent. A centralized task manager is structurally obsolete in advanced intelligence. This blueprint outlines the 5 non-negotiable hardware conditions derived from the math. Any physical substrate attempting to implement a DAN system must meet all 5 criteria. The system requires analog continuity to represent probability states without arbitrary rounding, and millisecond timing resolution to properly process gamma band phase coherence. It requires distributed local weight storage and asynchronous, event-driven computation. Nodes must only draw power when actively receiving an input signal. This precise sparsity is what enforces the 20-watt biological efficiency limit. The hardest engineering gap to clear is the bidirectional edge. Each synaptic connection must physically support both forward signal propagation and backward error feedback. Standard silicon processors cannot execute this locally. We have to look toward memristived crossbar arrays and next-generation neuromorphic chips to meet these material constraints. The roadmap to general intelligence is now defined by the physical ability to manufacture these bidirectional analog components at scale. We can evaluate the current paradigm of transformer-based large language models against these exact physical theorems. On the left, large language models process discrete token states and rely on a top-down shared global parameter server. They fail the continuous state and local weight requirements. They also rely on synchronous batch processing, computing across millions of parameters on a global clock. This breaks the asynchronous efficiency requirement. Pouring gigawatts of power into larger server farms will scale the output of a language model, but it cannot yield biological efficiency because the underlying architecture violates the physical requirements of local autonomy. To advance toward actual biological equivalence, research must shift toward decentralized, analog architectures governed by local physics. True general intelligence will not be coded as monolithic software. It must be grown as a mathematically autonomous physical graph.